Hi, everybody. Wonderful. All good. And then I just click next, yeah? Okay. All back. Okay, so I have been given the task to talk to you about how we do transmission spectroscopy or how we look at the observations of that. To start with, when we're looking at the transits, we're looking at the absorption of the atmosphere and therefore the transmitted light that we're seeing. So we measure the absorption of the different molecules in the atmosphere by the light, the absence of the light that they are blocking. And you can see we've got an example of Earth's atmospheric transmittance. This gives evidence for water in the Earth's atmosphere by the absence of light being transmitted down through here at these distinct bands. So we're looking at that blocked amount of light. And you saw this already yesterday. This is all going to be then directly related to the ability of that molecule to actually absorb that light. And that's related to the quantum transitions that you see for that. So they have to have those transition energies. And you can have a combination of lots of different kinds of energies. You've got the electronic levels, you've got the vibrational energy levels, and you've got rotational levels for those as well. So each atom and molecule will have that unique fingerprint on the light that we're seeing. And as a function of the wavelength, we can see the effect of these different types of transitions that we're measuring. So just simply from telling you what wavelength we've looked at, you can already discern what kind of physical process is occurring. So when we're looking in our optical and our UV, we're really looking at that electronic motion. We then go into our near infrared and mid infrared. We're looking at those low vibrational overtones of our molecules themselves. As we head out to longer wavelengths, we hit those vibrational modes. That's literally the stretching of the bonds between the atoms within our molecules themselves. And even longer wavelengths at the radio level, we're looking at the rotation of those molecules, so how they're physically moving around in space relative to that electromagnetic radiation that we're seeing. So you can already tell something about the astrophysical processes occurring in your object by the wavelength of light that you're measuring it at. Infrared absorption is one that we're really focused on now when we're looking at JWST spectra. And one of the key things to remember about infrared absorption when we're talking about these vibrational modes, the physical changing of the distance between our atoms and our molecules, that bond length, you have to have a molecule that has an electric dipole. So we're not going to be seeing absorption from nitrogen in the atmosphere around a rocky planet. It doesn't have the absorption features because it doesn't have that dipole. So we can't see certain molecules in this way. So we are limited in what we can understand about some planets. But what we can learn about is these different ones that do absorb the light. So showing you a graphic from Vivian Parmentier, and it is wrong. This is not what we do in transmission. This is a mission. Emily will tell you later. But it's a really good illustration of essentially what we're seeing. We are measuring the size of our planet. So if we look at the Earth-Moon system, we can see in real color the size of our planet and its atmosphere. If we go to different wavelengths, the physical size of that atmosphere is changing. The light that is being blocked is different. So we're seeing that change in the size of the planet. There is light being blocked. And essentially in transmission spectroscopy, what we're measuring is the area being blocked out. So the larger our atmosphere is, the more of it there is to absorb that light, the more light it blocks out, the easier it is to measure. The larger the cross sections of the molecules, so the bigger the molecules in the atmosphere, the more light they block out, the easier it is for us to measure it. And what we're critically doing in transmission spectroscopy, rather than looking at emission, so light directly from those planets like we see in the direct imaging, or if we see in emission spect, which we'll see in the next talk, is we're looking at what we call slant geometries. We are looking through a slice of that planet's atmosphere. So rather than looking normal to the planet's atmosphere, seeing through this column, of the planet's atmosphere, we're looking through an entire slice of that planet's atmosphere up to a certain pressure level in that atmosphere. So we're seeing through a huge, huge column, and this can increase the absorption significance of a molecule by over 30 times. So something that exists in the atmosphere at an incredibly low abundance can suddenly become incredibly significant when we're measuring it in our spectra. So we can actually access different molecules that we might not be able to see through other means. So I've already said that when we're looking at our transit transmission, we're measuring the relative area, and that's because we're measuring a time series observation of a planet as it passes in front of our star. We're measuring the change in the amount of light from our star as a function of time, and this tells us about the area of the light from that star being blocked. If we add an atmosphere onto this planet, what we're measuring is then the additional absorption from this annulus of the atmosphere around it. So we use the symbol here, H, and we'll go into a little bit about where that comes from. So you can see that when we're measuring this depth in our transit, we have our planet's area. So this is going to be some kind of base pressure that we're measuring. And we have this additional component which comes from the atmosphere of the planet itself. So where does this H atmosphere come from? What are we measuring here? How can we know the extent of our atmosphere itself that we're going to be measuring? So H is what is known as the atmospheric scale height, and it can be measured, calculated using this equation here. And it is essentially the height at which the pressure decreases by a factor of E. So let's look at an atmosphere. So the atmospheric pressure structure that we've got, we know hot air rises, right? But we also know it gets colder as you go up. How do these two things kind of fit together? So when we look at the Earth's atmosphere, so this is a nice example in this image, as we go up, the change in pressure with altitude causes a change in that temperature. So when we're seeing how that pressure drops, the way in which it does that is really, really critical for our understanding of what's occurring. So we're going to consider a column of air. So how and why the pressure is changing across this. If we look at a column of our air, we can say that the weight of our air is just the density times the area it's covered and that height of that column that we're looking at. So this is actually assuming that our density within our column is constant. So we actually have to make the change in our altitude very, very small. So our delta Z, the amount that we're measuring here from our base atmosphere to here is very, very small. So using this where we take it to our limit, we can actually say that the change in pressure with the change in altitude is equal to minus the density times the gravity of that planet. Now, if we take this and we start assuming that we're in hydrostatic equilibrium, so we're saying that there's nothing moving in the atmosphere as well. So we made a couple of assumptions here. That change in that pressure, we can then take our ideal gas laws and we can equate that. So if we're saying that it's in hydrostatic equilibrium, we're saying we're changing over a very, very small distance in our atmosphere, we can calculate that we've got these changes in pressure with altitude is equal to these two different kind of formulas with our pressure and then our density. Now, the critical thing is that in our density, we have to keep our temperature in that derivative because that might be changing with altitude too. And we know that it is changing with altitude. So if we take this forward, we can differentiate that with the height. And from that, we can get this equation here. So when we differentiate that with respect to height, we get this factor H out. And this factor H is then that our atmospheric scale height that I defined before that we're measuring as our annulus. So what is the amount of atmosphere that we're measuring around here? And you can take that through. You've got our ideal gas laws in here. You've got the different formulas for that. And this is traditionally the one that we use in planetary science, in exoplanet science, is the Boltzmann constant times the temperature of our atmosphere, our planet, divided by the mean molecular weight. So mu here is the mean molecular weight of the atmosphere, and then the gravity of the planet. But remember, we are again assuming hydrostatic equilibrium and a small change in Z. We are assuming that gravity isn't changing throughout that column that we're measuring. And we're assuming a single temperature profile. The other thing that we need to understand when we're looking at our spectra is the optical depth and the cross sections that we're looking at. I told you that the larger the cross section of our molecule, the more it's going to be blocking out the light. So the optical depth is something that is a dimensionless measure of basically how much stuff is the light going through. And you need to take into account the modifying effects of the mass extinction of the air that you're passing through. So it's a density and wavelength specific value that you've got. So you can see in this equation here, we've got our optical depth and we're integrating it over our atmosphere here. We've got our mass extinction coefficient, we've got the density, and we've got that change in altitude that we're looking at. In our slant geometries, this actually becomes really dependent on our absorbing cross sections and the volume density of our atmosphere. And then again, we can see this factor coming in here of the area of the atmosphere that we're measuring. So the optical depth itself, dependent again on our wavelength and our altitude, can be measured from what we're getting in our transmission spectra. So for the Earth's atmosphere, compared to the normal geometries, we would get something like 75 times that of the column of air we're looking through at these slant geometries. You can then calculate the effective altitude that is being measured using these different components and understanding a bit about our species abundance. So how much of the material do we have in our atmosphere? What is the cross sections of our atmosphere, our optical depth? And again, we've got scale height in here, so you can see the components of our scale height throughout this equation. Okay, so we've got all of that. Let's start having a look at some actual spectra and what we've been measuring. So first off, I have just taken all of those wonderful 5,000 plus planets and I've narrowed it down here to just looking at ones where we have a mass and a radius measurement. And you can see it on these two very traditional diagrams of semi-major axis along the bottom versus our planetary radius, and then planetary radius and mass here. So you can see our solar system in context. Within the mass radius diagram, we're really probing those kinds of planets. But in terms of their orbital distance, we're really not looking at solar system analogs here. Just putting on top of this what has been selected in the transiting observations for cycle 1 in red and cycle 2 in blue. I think that's the right way around. So this is the distribution of planets that will be observed or has already been observed with JWST. So keep that distribution in mind. So how do we go about this? You'll be doing this, you've done some of this yesterday and you'll be doing some this afternoon. We're taking our 2D images. This is a spectrum that we get from the NIRSpec instrument on JWST. We go from our 2D images to extracted one-dimensional stellar spectra as a function of time. There is about 4,000 different spectra all lying on top of each other there. It's beautiful. They actually lie on top of each other. That is a nice key component of what we're doing. We then, from that, we get our light curves. So we're getting our broadband light curves here, looking at different aspects of that. So in this light curve, we've got something which is called a mirror tilt event. You see a jump in the flux here. During our observation, something's happened on the telescope we have to deal with. And there are a number of different things that we can measure for our telescope to try and understand how we can detrend our observations with respect to systematics or things that are happening on the instrument, things that are happening on the detector, or things that are happening on the observatory as a whole. We can then take these, we can break our observations down into our spectroscopic light curves, and we fit for those. So you'll be playing around with fitting those this afternoon. So fitting for those systematics and detrending our light curves. And then from that, we get our planetary spectrum at the end. And you can produce a planetary spectrum using many, many different kinds of combinations of this. So what process do you use to get from here to here? What different detrending parameters do you use to get that? And you can see here, we've got, I think there are 4 or 5 different measurements of this spectrum, this planetary spectrum, with different techniques that have been done. So we can make comparisons between different ways of treating our data and see what our results, how our results change with those different methods. And one of the really key things about doing those different fitting methods is it comes in a different kind of set of stages, and they can be simple, they can be complex, they can be quick, they can be slow. So thinking about how you're treating those detrending, how you're fitting your light curves is really, really key. And we can break it down into very basic, this is a very basic picture of what you'll be doing later, is looking first at our systematic model. So are we using a simple systematic model where we assume just a single model that is describing what is going on at our observatory, our instrument, at our detector level, and we're using that to detrend our light curve? Are we fitting our white light curve and then subtracting all the residuals off of that and assuming that that is wavelength independent? Or are we going to something slightly more complex? We're looking at perhaps some combination of different engineering parameters. We're looking at a series of different kinds of models, fitting them all, and using the evidence in our data to describe which of those models is most realistically fitting our data. Or we can use machine learning techniques such as Gaussian processes as well. We then put that through our solvers with our transit model, and we can go very, very basic with least squares minimizers. Is incredibly quick, but it can get stuck in local minima, so there are downsides to certain different techniques we use. We can use MCMCs and nested samplers, or again, a GP also incorporates these two kind of parts of this. And in the end, these give us different looks at how we're treating our uncertainties and what we're seeing. And one of the key things when we're looking at how we're fitting our data is the fact that the larger the suite of models that we consider, the higher the likelihood that one of those models is actually describing the truth. So whether we like it or not, we don't actually know absolutely everything that is happening to our light as it comes through our telescope, the detector, and as it's going through that instrument path. We don't know every single aspect of our telescope that is affecting the measurements we're making. So how can we decide which one is the best? Unfortunately, every single one of these does require that one of our models is assumed to be correct. So when you're looking at your answers, remember, there are still assumptions built into that, whether we like it or not. Jump straight to the results of some of this. I want to show you the history of what we've been doing over the last decade. This is our mass radius diagram again, but now beautifully filled in with spectra from tens and tens of papers that have been published, from the tiny little rocks with apparently no air. We'll find out. All the way up to these amazingly beautiful spectral features that we've been seeing across the mass and radius range. And what we've seen from our measurements with the Hubble Space Telescope is that water is absolutely everywhere. And 80% of the planets that we have measured, we have detected the presence of water vapor in the atmosphere. But often that detection, that absorption signature, is muted by around a third of what we would expect to see. I want to now tell you a little bit of a story, a very scientific kind of journey that we've taken with one particular planet, and that is WASP 39b. It is a Saturn mass Jupiter radius planet. And we originally looked at it with the Hubble Space Telescope, looking in the optical. And what we found was the presence of very strong absorption from sodium and potassium. Sodium and potassium are a beautiful example of that slant geometry. Their abundances are incredibly low. But we're looking through 30 times the amount of what we would see at normal geometry. Those absorption features are huge, and we can really, really nicely measure them. So from these measurements of those sodium and potassium features, we predicted that we should see strong absorption from water vapor in the atmosphere. And that is indeed what we saw. So with observations then in the near infrared with the Hubble Space Telescope, we then saw water absorption features, 3 very distinct bands of water absorption. And from this, we predicted that we should see strong absorption from CO2. So we did observation, prediction, observation, prediction. Welcome to the ERS program from the Transiting Exoplanet community. Not only did we get that beautiful absorption from the CO2, but we were able to really start to try and understand JWST in all of its instruments. And we looked at this planet across all of the different wavelengths from 0.6 microns with our nearest SOS observations, again, capturing those amazing water absorption features, out through NIRCam, near spec, which takes us all the way up to 5.1 microns. And then in addition to this, we got prism observations, which covers that entire range at a low resolution. So we've got confirmation again and again and again from this planet of observation, prediction, observation, prediction. And in addition to the measurements that we've made here of those predicted features, we also saw some absorption from something that we didn't expect. And you can see it just down here in this bump here and over here in this little bump next to the pink feature. That is absorption from SO2 in the atmosphere. And that SO2 was really sent our theorists reeling, and I think be prepared, we're going to do this to you continuously for the next 2 decades, so have fun. They then went away and they had to look up the photochemical pathways that needed to exist for this amount of SO2 to exist in this atmosphere. It wasn't predicted to be there. But it turns out that it is there, and there is actually history of trying to understand the presence of sulfur species. So perhaps we should have expected it to be there, because there are a number of different papers looking at the presence of sulfur species in these atmospheres and where and in what conditions we might see them. And again, we come back to the beauty of this scientific process. We had observation of this SO2, and then we predicted the presence of SO2 in MIRI observation. So in the mid-infrared, it should absorb even more. And the team went ahead and got time to do that. And we'll see a paper coming out very soon looking at the SO2 in the MIRI wavelengths. So it's a really nice story of exactly what you guys should be doing over the next couple of decades is observation, prediction, observation, prediction. And I'm afraid that I do think that the theorists will be chasing the observers the entire way. Another thing that we can do with some of the JWST spectra is we can look at some higher resolution observations. So with the near spec instruments, we can get to an R of 2,700. And with this, we can start looking at some of the fundamental band structure of different materials using cross-correlation techniques, or simply using these kind of summation of the in versus out of bands for things like CO and methane as well. It should work if we find methane. I believe we have. So you can see that we've got our CO model, our CO bands, and we can see which observations are in band versus out of band, and we can measure the difference between those. So we can use these slightly higher resolution observations to really look at that fundamental band structure. Now I'm going to leave this for Natasha at the end of the week, looking at these smaller planets and what we've seen. You can talk to Kevin Stevenson later. But one of the really key things is that we're seeing that there is going to be some challenges associated with this. And one of the challenges can be really broken down by optical observations. So I'm going to push you for Hubble observations as well, because the optical and the ultraviolet can really help us understand the stars and the clouds in these atmospheres. And we've been looking at evaluating that wavelength dependence and understanding the role that these optical observations are going to be playing in trying to really interpret what we're seeing in the infrared with JWST. Wavelengths below 0.6 microns are really, really key for us understanding the clouds and the stellar contamination in our spectra. Clouds are going to be appearing continuously. They are not bad news. They are excellent. And you know why? Because JWST can get us information on exactly what it is that we're looking at. I think that we're going to be starting to understand and see a lot more about what can we get from our observations in terms of the chemical properties of our clouds, the particle sizes, the distributions, and the altitudes in which they are absorbing that light. We're going to see vibrational mode spectra. We're going to see these molecules. We will see absorption from different species. So we can start learning more and more about what those species are and how they're impacting the gas phase structure and abundances that we've been measuring. Just to give you a snapshot, because it was promised in one of the talks yesterday and I hadn't put it in my slides, of what we've kind of measured so far. This is a very old snapshot, and you should go to NASA Exoplanet Archive, which now contains all of these spectra and more, and make your own just massive diagrams of all of the observations that we currently have of exoplanet atmospheres. And you can see we're starting to try and understand and measure the abundances of these molecules relative to different measurements we've made before. I'm going to finish up on this, which is just some high-level thoughts. People seem to really like the near-spec observations. They like those wavelength range, looking for the higher resolution observations that we can get. You guys are the ones that are leading the way here. So lead. You have the ideas. You have the drive. Do it. Take us forward. What is the holes in this parameter space that we've got? What do we need to know so that we can start to understand what this means? I'm going to leave it there, and I will take questions here and online. So thank you.
All right. We have a few minutes for questions. Maybe we can start from someone online, if there is.
So we have this online question asked, do we have anything to fix the data jump gap caused by the tilting of the mirror?
Yeah, so the mirror tilt events can be fit very easily in our spectra. They actually imprint themselves on the full width half max, so the spectral trace themselves, and we can use that to decorrelate it, or we can just do a simple step function. So you can see different ways that you can use to decorrelate that already, and that fits into that whole story of, do you use a simple model, which would just be saying it's a step, we're going to fit for an absolute step, or do we want to fit something that is related to parameters that we've measured on our detector itself, so the full width half max. So you can already see there are different ways of dealing with that, but there are ways of correcting that. The telescope is not damaged in any way when we see any of these kind of mirror tilt events.
I'm just going to ask another online question. This question asks, what kind of velocity law is considered while generating the models to the H2O absorption lines?
So what kind of velocities were assumed when we're measuring those?
Yeah.
Okay. So when we're looking at those broadband spectral features, we don't need to consider the broad velocity of the system. But when we go to those high resolution ones, for those CO bands that we're seeing, that fundamental CO band, you do need to shift it to the velocity of the system itself, which includes the velocity of the telescope. So you do actually need to correct for those different positions that you've got, so you can get those absorption bands at that high resolution.
Right, regarding the importance of using Hubble to complement JWST observations, could you compare the utility of UVIS versus STIS and what information you get in the different wavelength ranges?
So when it comes to the UV, a lot of our chemistry is driven from the ultraviolet. So understanding what is going on in these atmospheres in the ultraviolet is going to be key for us understanding exactly what's going on at these longer wavelengths. In addition to that real chemistry driver that happens, we're also seeing the influence of the scattering properties of these clouds. So we see the broad kind of properties of the clouds themselves. We don't know what kinds of clouds are causing it. So scattering is generally indicative of small sub-micron sized particles that are scattering that light. flat spectra throughout the optical is generally larger particles. And the question that we have is, what kind of size distribution do we have of those particles? And therefore, what kind of vertical mixing might be responsible for that? So you got to think about the dynamics of the atmosphere and the ability to sustain and suspend particles at those altitudes that you're measuring. So you can get a kind of influence from that. And then when we go to the infrared, when we're tying that into the infrared, those scattering slopes are really going to help us understand whether the absorption features that we're seeing in the mid-infrared are in fact from clouds in the atmosphere, because they are inherently tied together. Small scattering particles will have larger absorption in the infrared. So if we're seeing both of those things, you can really tie it into the clouds that we're measuring.